All right, let's talk about arc length. Arc length is the distance from this point to this point. Again, we can really start anywhere we want. You're given some function, and you're interested in this total length, right? If you laid the string out on that exact curve, and then stretch the string out, how far would the string be? So how do we figure that out? And it really boils down to just the Pythagorean theorem. So going from here to here is going to be pretty difficult, but let's imagine doing it in really, really, really small steps. And so we would break this up, and let's say we broke up the step from, let's say, here to here. We wanted to figure out that particular distance, and we could break it up even more. But this is some distance, right? Some d. But then this is some distance, and this is some distance. So we'll call that what it is. That's delta y, and that's delta x. Okay, so what's d? Well, d is really easy then. D is just the square root of delta x squared plus delta y squared, right? That's just the Pythagorean theorem. Well, what is then the total length of this? Well, what if you broke this up into an infinite number of these things? Well, how would you find the total length? So the total length of this guy, which we'll call L, and again, we'll go algebra first, and then I'll change it to calculus at the end. It's the summation of all the little bitty distances. Okay, that's pretty easy. If I break this up in a bunch of pieces, the total length is just the sum of all the pieces. Each individual piece is just the Pythagorean theorem. I go a little bit to the right and a little bit up, that distance, that straight line distance. And again, if you break this up into really, really small segments, all these are really bitty lines, then they're all really, really, really small triangles as well. Okay, and that's the theory. We're really done. The rest of this is me just manipulating it to make it into a form that we can actually use. Right, so this is the sum of this. And what can I do to this? Well, I can multiply top and bottom by anything I want. So let's take delta x squared plus delta y squared, and I'm going to multiply by delta x over delta x, right? I'm not changing the value of anything. I'm just multiplying this, and you'll kind of see why in a little bit. But if I multiply top and bottom by delta x, I then can write this. And what I'm going to do here is I'm going to take this delta x, and I'm going to move it inside the radical. It's in the denominator, and so I'm going to write it as delta x squared plus delta y squared all over delta x squared. This delta x stays put. And some might think, well, why is it delta x squared? Again, you took this delta x in the denominator and moved it inside the radical. So inside it's got to be delta x squared, because the square root of delta x squared would give you back just a delta x outside. Then I'm going to write this as two separate fractions. This is delta x squared over delta x squared, which is just 1. Then this is delta y squared over delta x squared, which is delta y over delta x squared. And now I'm going to change it to calculus. So instead of the summation, I'm going to write big boy language, the integral of the square root of 1 plus, now what's delta x over delta y? Well, that's just the derivative, dy dx squared, and then instead of this lonely delta x, I write a dx. And there you have the formula. And certainly you're integrating from some x value to some future x value. Okay, so again, the theory behind arc length is really easy. It's just the Pythagorean theorem. We're going to take this curve and we're going to break it up into an infinite number of really, really, really small segments. Each segment has a certain distance, which is the Pythagorean theorem. The total length then is the summation of those distances. I have a little algebra trick that I multiply top and bottom by delta x. I move the delta x inside the square root, making it delta x squared. I then separate those fractions. Delta x squared over delta x squared is just 1 plus, and then this is delta y squared over delta x squared, and then I change it to calculus. Instead of a summation, it's an integral. Instead of deltas, their d's, and now I have the idea of how do I find arc length in Cartesian coordinates, meaning x's and y's. I take the integral of the square root of 1 plus the derivative squared dx. Okay, now do an example. So let's say I'm looking at the curve sine x. Okay, y equals sine x. And I want to figure out, if I wanted to put this together, how long is that? Let's follow the formula. The arc length of one arch of sine is the integral from what to what? Well, starting at 0, of course, and then when does sine get back to 0? And that would be pi. So I'm going to integrate from 0 to pi of the square root of 1 plus the derivative squared. The derivative of sine is cosine. So cosine squared dx. All right, and when you type this in on your calculator, this isn't an integral you're going to be able to do analytically, meaning by hand. You're going to have to use Math 9 and bust this up. And when you get this, you're going to get an arc length of 3.82. And that's a reasonable answer. Here's why it's reasonable. What if you assumed that this was a circle? Again, it's not a circle. It's a sine function. But if you assumed that it was a circle, it would look something like this. And if you found that distance, well, that would just be 2 pi r. And if you assumed it was a circle, it would have a radius of 1, which would mean, oh, my bad, it's a half circle. And then you would get pi times 1, which is 3.14, right? If it was a circle, and it's not, then they would have a total distance of 3.14. And it's not a circle, it's bigger. This arch is bigger, and so 3.82 makes reasonable sense. Okay. What about, how about just x squared? What if I wanted to know it from, I don't know, 0 to 4, let's say. So 0 to 4, right? This point then is going to be 4 comma 16. Again, I'm looking at the curve y equals x squared. This is the point 0, 0. Okay, and how do I figure it out? Well, the arc length, meaning the distance from here to here following the quadratic, is going to be the square root, the integral from 0 to 4 of the square root of 1 plus the derivative. The derivative of x squared is 2x squared dx. Type that in on your calculator and you're going to get an arc length of 16.81. And again, we can do a common sense check on that. This curve length is probably fairly similar to the straight line distance. The straight line distance would just be 16 squared plus 4 squared, right? This distance, the dotted distance, would just be the square root of 16 squared plus 4 squared, which is 16.49. And again, our true arc length is 16.81 because the red is a little bit longer than actually just going on that straight line. So again, kind of verify that it makes some common sense checks. Okay, so when doesn't this apply? Well, it's going to have a couple issues. Right? Easiest issue to kind of look at is what would happen if I looked at this curve. Y equals the cube root of x. Okay, if I look at that particular curve, I'm going to get something that looks like that. Okay, and let's say I was interested in going from -8 to 8. Okay, so let's put points on there. Right there, that's 8 comma 2. Right, if you plug in 8, the cube root of 8 is 2, and then over here, I get -8 comma -2. So let's say I wanted to know this distance. Well, a tricky thing happens. The derivative doesn't exist at 0. And so if the derivative doesn't exist, how are you going to integrate over that? Right? Normally we would say L equals x1 to x2 of the square root of 1 plus the derivative squared over dx. But how are you going to integrate from -8 to 8 when the derivative doesn't exist on that interval. So we're going to have issues. But have no fear. All we have to do is flip it. Instead of thinking about x's, we just think about y's. So we take this and we say, well, if y equals the cube root of x, then x just equals y cubed. This formula clearly is symmetrical. If you look back on what I did here, take this first sheet back, I could have multiplied top and bottom by delta y here, and then everything would have been in y's. It would have been delta x squared over delta y squared plus 1 times delta y. So I could have just done the opposite, and I would have got the y formula. Well, the y formula is the same thing, except you'd integrate from some y value to another y value of 1 plus dx dy squared dy. And that's just the derivative of x with respect to y. It's just flip-flopping it. But that's really easy because the derivative of the derivative of x with respect to y, instead of being infinitely big, now it's just 0. There's nothing wrong with the derivative of 0. There was just an issue with the derivative not existing. So what are we going to integrate from? Well, I have those 2 points there, as I'm going to integrate from this y value to this y value. So instead of negative 8 to 8, I'm going to integrate from negative 2 to 2 of 1 plus dx dy is 3y squared. Right? I'm just taking the derivative of x with respect to y squared dy. And if you type that in on your calculator, you're going to get 17.26. And again, there are some issues. Again, it doesn't come up much, but if you have a derivative not existing, then you're going to have to deal with it. Sometimes you break it up into 2 separate integrals. In this case, we can just flip-flop, and instead of integrating with respect to x, we can integrate with respect to y. When we integrate with respect to y, we're going to use the y bounds, and we're going to use dx dy, which is the derivative of x with respect to y, right? It's just the opposite kind of derivative there, and then we get the arc length. Okay? Again, arc length is just the Pythagorean theorem. We sum up all the little bitty distances and we get the total distance.